get married, you have to take care of the children. No. Everyone have to work. Oh, I also have to work. I got up about before 6. Okay, we are going to cover this. Should be very fast. I think we should finish it today. Electromagnetic induction. Right? We are going to look at the laws of electromagnetic induction just to review. I think we have gone over it last week. Then we want to define a new quantity called magnetic flux. The unit is Weber. And that's how we define it by this formula. And you're supposed to know how to use this formula and memorize this formula. Then another term, magnetic flux linkage. Total. This is for one coil, this is for many turns. Then experiment. Right? And then these are the two essential laws you have to memorize. Faraday and Lenz's law. And then some simple application. So Friday, we will discuss electromagnetic induction. Wednesday, your test. Remember magnetic field. Okay, I'm starting to give you every week test. So after that, we could go to review for your last semester's work, circular motion and gravitation, all that. So get you all ready for the mood for the exam. It's good you all start early, because if not, you start somewhere after middle of June. That was the original plan. Sorry, you got people coming in. Right? If you start original plan, is very rushed by the time, and then you got a lot of holidays, and then by the time you all get back and your trial exam is coming already, and after the trial exam is your revision, your parents' day. Before that is your parents' day. Parents' day trial exam. Then after that your revision. And then October onwards will be your exam. So you can see very short time only. Only you come back now, then more time to study. No need to rush too fast. Physics, you are okay. We can slow down, let you ask question. Okay, the main purpose is study electromagnetic induction because we generate electricity. Yeah, using electromagnetic induction. And then we want to study the laws. Right? So basically, we'll look at this one, where you use coal, you heat it up with water. And some of you are struggling because your internet connection is a bit poor. Right? So as I suggested, you may want to consider coming back to college and use the computer lab there. Right? You find problem with your internet, after all it's cooler, and then can study there. Very quiet, plenty of room for you to study. You will see very few students around. Okay, so anyway, what is happening will be the water heat up becomes steam. Steam will cause the turbine to rotate, and then that is where your generator is, and then electricity is produced. Okay, so that's roughly the. Okay, anyone, what is missing here? People still waiting in the room there. Hey, what happened to her? She's having problem coming in. What is missing here? Anyone? That's your mercury. That's your conductor. What is missing? It's called Faraday's simple motor experiment.
The coil.
What coil are you talking about?
I don't know.
I just told you all the page and you got somebody asking me the page. Not paying attention, that's the page. Okay, that's the page. 264. Anyone? What is missing?
Magnet.
Thank you. You are right. Magnet missing. No magnet cannot work. Right? You need to have your magnet there to provide a north and south pole. And then because of the electric field, there's a force on this conductor. Force it out. Right? That's why it can move. Okay, let's carry on. Right? We have introduced this topic where we move the rod down in a magnetic field. Right? That's what it means by induction. Right? Because we move it, we cause the current to flow. Right? That's why we induce, we produce, right? Produce. Usually we use galvanometer. Essential cannot use ammeter, right? Because the current is very small. And since we can move up and down, the current can go positive or negative. So that's the reason why we have to use a galvanometer. Can read both direction for the current, and you also can measure small current. Okay, so in this case, we move mechanical energy, which is motion, to electrical energy. I can say kinetic if you want to, but usually we prefer to use mechanical because potential may still be involved. Okay, so the first basic quantity, the first quantity that we use for this topic will be magnetic flux. Right? B is magnetic flux density or magnetic field strength. So it is the product of magnetic flux density and area. And that BP must be perpendicular. Right? Perpendicular component. That means that component must be perpendicular to the area. Okay, so if it's this case, the area is usually the coil of wire, then A times B is your flux, magnetic flux. Right? If it's at an angle like this one, an angle theta to the surface, B is an angle theta to the surface, then we just find the vertical component, or we call it normal to the surface, and that is your far away from the theta, so it's B sine theta. Okay. Right? Sometimes we need to use not only one coil, we need to use many turns or many coils. Then in this case, we introduce the next term, magnetic flux linkage. Linkage means total passing through n turns. Right? So it's one is BA sine theta, then n turns is times n. No? And then we can picture, if you like, B, right, magnetic flux density as the number of lines passing through unit area with a direction, right? Number of lines, right? As we represent B by lines with direction, right? It's a vector quantity. Whereas magnetic flux, we are interested in the total number of magnetic field lines passing through that area A, that's all. And it's a scalar. Okay, it's a scalar. That's a new term, physics 5. The reason why we have scalar, A is not a scalar lah. If you go to university, A you learn that it's a vector lah. That's why vector times vector can become a scalar. But you don't need to go that far lah. You just learn to accept that B is a vector, right? Magnetic flux of phi is a scalar. That's all. Okay, and we go to the unit. B is Tesla, A is meter square. So instead of calling it Tesla meter square, we give you a new name, Weber. Right? Weber, W-E-B-E-R, Weber. And we say it's a 1 Weber is a magnetic flux, or the unit area. Unit area means 1 meter square. where the magnetic flux density passing through is 1 Tesla. So 1 Tesla and 1 meter square. Okay, or sometimes examiner will accept that. Just a short form there. Same thing as write it down. So the magnetic field strength of the Earth is very low. Micro, 30 to 60, depend on the where you measure it. And then you need to calculate. Okay, you are given the cross-sectional area. And you are given the magnetic field strength passing it. And this is the angle theta, 50 degrees. Then you want to find the magnetic flux to the surface. Exam is also that simple. Basic formula memorized, use it. Right? So sine theta, theta is 50. Put inside there all the value. Change your P to Tesla. So 10 to the power minus 3. And then this one, 35 cm squared. Change it to meter. Right? So it's 10 to the power minus 4. And sine theta, that theta is 50. 50 there. Multiply out. Get our answer. Okay. Stop and ask. Don't keep quiet. Okay, experiment. This is a common experiment which you have seen in your SPM, or I've shown you last week. You have your magnet. Right? You push it in, and then you can find the direction of the current. Okay, so basically we have a coil or solenoid. Right? This is probably a cardboard if you want. Right? Remember, this is not a metal, this is a cardboard. Just to so that you can coil on it. And then this is your galvanometer. And then we push a non-pole there into the coil. Then we observe the current. And then from our observation, we know that the current at this end will flow in the circuit such that this one will be what? If you push South pole in, this one will be what? South. You want to repel. You want to opposite. Right? So we can, from our right hand rule, we can know that this is south. Right? The current flowing there, we can know this is south and south repel. So we can come to a conclusion, direction of induced current flow such as to oppose. Right? This current will flow in this circuit there. So that this one becomes a south pole to oppose the south pole that's coming in. Okay, let's just go over the explanation. Push the south pole of magnet into the coil. Current will flow in such a way that the pole of this coil facing the magnet is a south pole. That means repulsion. Right? That means the induced current will flow. Basically, we have mechanical energy here. When we push it in, induced current flow, it means it becomes electrical energy. Then, as I say, we can use our right-hand grid rule to show that this is a south pole. Right? And then we also need to know if you push in, you are applying a force, but the repulsion is an opposing force. The two forces are equal, so that your speed is constant. Right? You push in, the speed becomes constant. If you want to go faster, you have to apply more force, and there is more force opposing you. Right? So the force pushing in and the force opposing you is the same, equal and opposite, action and reaction forces. That's why you make the speed constant. Okay. Same. Basically, Lenz's law is a statement of conservation energy. Basically, energy transformation, we push in, right? The south pole into the magnet. That's mechanical energy. We do work. We push it in. Or kinetic energy. Then we have induced current. Right? Flow in such a direction that this becomes a south pole. Repulsion. So that is your electrical energy. So mechanical energy change to electrical energy. Right? That's the reason why we say Lenz's law is a statement of conservation energy. If the magnet doesn't move, there's no current flowing. Okay, so normally when we want to summarize a law, we must give it a general statement. We cannot use it for just that specific case. Right? We have to use a general statement applied to a general case. Put a south pole or magnet into the coil, induce current flow in the coil, so that this part becomes a south pole. So we can summarize this one. Right? The induced current or EMF will be established in a direction so as to produce the effect. Right? That means as we push it in, the current will flow, or the EMF. Right? Where there's a current, there must be an EMF. We call that induced EMF. Right? It will flow in such a way that which it will cause which oppose the change producing it. That means the current will flow to oppose the change. This is the change. This is the one changing it. Right? Current flow to oppose this change. So that is the general statement of Lenz's law. Memorize, no choice. Okay. Any induced current or induced EMF will be established in direction so as to produce effect which oppose the change that is producing it. Okay, and remember that Lenz's law is a statement of conservation of energy. Okay, 3 ways in which the EMF may be induced in a coil next to a current carrying conductor. Right? We can either use a magnet or current carrying conductor. Current carrying conductor also produce magnetic field. Magnet also produce magnetic field. So basically, we just go to the formula and see how we can produce induced EMF. Right? If there is your wire, there's your coil. Right? We can vary the current in the wire. Then we will have induced EMF in the coil. Right? Remember your magnetic field around the wire, current carrying wire. You can get it from your right hand grid rule. Sorry, I'm trying to position my hand correctly. There you can see right hand grid rule. Right? Right hand grid rule. So it's coming, in this case, it's coming out. At the coil there, the field is coming out. So if this is the current is changing, then the flux, magnetic flux is changing across the coil. So EMF will be produced across the coil. Right? So we can switch out the current on and off. Or we can use alternating current. That means the current changes direction. Or we can move this coil. Right? This coil towards or away from the current carrying wire or magnet. Right? Same as here that we have done. We can move the coil or we can move the magnet. Either way, we will produce an induced EMF. Right? So basically here we are just changing the current to produce a field. Right? We change the current, we change the field. That's what we are doing. So in this case, we change the current. In this one, we change the field. Okay. What other ways? Yeah, we can also have a coil there that's rotating. Right? So in this case, we change the area. Right? We change the area, we change the flux. Right? Rotating coil. Or in a transformer, same thing. Right? We change the current here in the primary. And when we change the current in the primary, we change the magnetic field here, the lines, magnetic field lines here. And when we come to here, it becomes the magnetic flux, this one, magnetic flux. So we change the current, we change B, we change the flux. And we have a light there, or current flow. Okay. Transformer, we change the current primary, we change the magnetic field, then we change the magnetic flux through the coil here. Then EMF is induced in the coil here. We call secondary coil, which is our next topic after electromagnetic induction under alternating current. How do we increase the EMF? Same thing, right? Increase by increasing the strength of the magnetic field. Easier to use electromagnetic lah. Then we can change the current in the electromagnetic. Okay, in 10 minutes time, we'll give you 5 minutes break. Or increase the speed, moving in faster, or taking it out faster. Increase the number of turn. Right? Number of turn here. So remember the field, the flux, or the field, magnetic flux density from the magnet is stronger, the pole there, and the farther away. So before it enters, this part is lost outside. It doesn't go in. But as it moves in, more and more flux will cut the coil. That's why you have the increased EMF, right, as it goes in. So this is the next formula that we are going to introduce. Right? We summarize it under Faraday's law. This is the change in flux linkage divided by the change in time. It means the flux linkage will change during this time. Sometimes we use T, sometimes we use delta T. Doesn't matter. It's just an understanding. Right? And that flux linkage is just your BAN. So if we can choose what we want to change. We want to change the area. As we're rotating coil, we change the area. Or we can change B. Right? So it depends. N is usually constant, number of turns here. So when we increase the speed, we increase the rate of change of magnetic flux, magnetic field there. Right? Make it change faster. That's all. So we summarize it in Faraday's law. EMF induced is proportional to the rate of change of magnetic flux linkage through the circuit. Through the circuit. No circuit, current doesn't flow. Right? We can summarize it. Wherever a rate is a calculus form. But because your examiner prefer this way, right? They want to remove all the calculus there to not frighten some of you who didn't do additional maths. So they usually prefer to write this way. Change in flux over the change in time. Why the negative sign? Represent Lenz's law. Right? The opposition was discovered in 1831 in England by Michael Faraday, in America by Joseph Henry. So if you go to America, they promote it as Henry's law. You could go to England, you promote it as Faraday's law. Right? So be familiar. Right? For those who are going to America to study. Right? So E and phi are not in phase. Right? You can see that from here. From here. Right? That's the rate of change. It's not easy to see from here, unless you use calculus, which I'll do in a while. Right? They are not in phase. In phase means E equals to like K times flux, but it's not. It's not K times flux. Okay? There's a negative sign there. Negative sign shows you it's not in phase already. And then you should be able to say, right, this is a gradient. E is the gradient of the phi against T graph. Right? The EMF can be obtained from the gradient of tangent to the graph phi against time graph. Okay, Let's try to understand the term. If it's E, if it's not true, okay, I'm just trying to explain to you. E equals to K phi T, K is a constant, then we can say these two are in phase. That means phi and E are in phase. That means as phi increases, E increases, but that's not our case. Or if you got negative sign there, same thing. Right? If you got a negative sign there, they are not in phase already. Straight away we know 180 degrees out of phase. Right? Or if you want to use mass, usually your flux linkage changes. Right? I prefer to use sign. I can use cos A1. And then when you differentiate it, it becomes right? Differentiate it, this one is 0. So when you differentiate this one, it becomes cos omega t. Differentiate omega, it becomes omega. Right? So we can see there's a negative sign there. And this is sine, this is cos. So they are not in phase. Right? Straight away, they are not in phase. Right? So that's why I say mass is easier to see. You try to explain it harder, but with mass it's easier to see. Okay, more or less completed. Right?
So
Generator. Right? Let me just
So can you go back one slide?
speak a bit louder.
Can go back one slide?
Go back one slide, okay.
The phi t is the
Phi t there, phi t.
linkage.
This is a flux linkage. Usually it's
Then the phi
alternating because we use alternating current.
Then what is phi o?
Say again.
Phi o. The
Phi o is the maximum value. Maximum value. Amplitude, if you like, amplitude. Anything else?
yeah.
Okay, if nothing else, let's just watch the video. Right? In case you got cut off, then you got just take your 5 minutes off.
Welcome to the video tutorials of Mechanismuller. This animation authored by Dr. Sehan Ersoy is the property of the client GDF Suez and subject to copyright limitations. We thank GDF Suez for giving us the permission to publish this video. There are 3 major types of water turbines. The Pelton turbine requires large water head and low flow rate, and the Kaplan turbines require low water head but large flow rate. The Pelton turbines usually built in mountainous regions, while the Kaplan turbines are located in lowlands. These restrictions make these two-kind turbines less common than the Francis turbine. The Francis turbine fills a large gap between the Pelton and Kaplan and it is widely used. They operate in water head from 10 to 600 meters, and primarily used for electric power generation. Their power output can be calculated from the water head and flow rate and typically range from 10 to more than 700 megawatts. One of the distinct advantages of the Francis turbine with respect to other water turbine is that they can also be used as water pump. This makes them ideal for the pump storage systems. This animation shows the operation of a Francis turbine in a dam. The arrows show the water path and direction inside the dam. The water from reservoir behind the dam transferred to the turbine by a penstock. The penstock diameter of a Francis turbine could be as large as 10 meters. The water coming from the penstock is transferred to the inlet scroll, which distributes the water equally around the wicket gates. Water passes through the wicket gates, which controls the amount of water passing through the turbine, before reaching to the runner. This in effect controls the power output of the dam. wicket gates also adjust the angle of the water reaching to the runner. After passing through the wicket gates, the water reaches to the runner. The water pressure forces the runner to rotate. The rotation speed of the runner can be in the range of 80 to 1000 revolution per minute. The water continues its motion downward under the runner to the exit pipe. The exit pipe discharges the water to the environment as low-pressure water. The turbine
Okay,
shaft
we
of the
will
Francis
stop now,
turbines is almost
so you
always
can
mounted
listen it to
vertically.
it yourself in your free time.
This makes discharge of the
Take your
water
5
much
minutes break.
easier due to swirling effect of the water
Take your 5
in the
minutes break.
inlet scroll and the effect of the gravity. The rotation motion of the runner is transferred to an electric generator shown in here. The generator